So welcome everyone to the 519th Brookhaven Lecture. I'm Björn Schenker. I'm the chair of the Brookhaven Lecture Committee. And just a quick few words about the Brookhaven Lectures before we get started. So the Brookhaven Lectures, which have been held at Brookhaven since 1960, so they're meant to acquaint the listeners with new developments and ideas in all fields of science at the lab, and make people at the lab aware of the aims and potentialities of Brookhaven National Laboratory. And giving these lectures is not an easy task, and it's very different from the more specialized talks that many of us are usually giving. And so it takes the lecturers quite a bit of work, and they have to really see their work within a wider perspective. And the lecture committee works with every speaker before the lecture to ensure that the level is appropriate for a non-expert audience. So I'm very thankful for every speaker that agrees to take on this challenge, and also for the committee who helps preparing for all these talks. We plan a Q&A after the talk, and to ask a question, please look at the bottom of your Zoom window for the Q&A button. There you can enter your question, and in the end, I will either ask you to I will let you unmute and ask a question, or just read the question. Also, in the end, there's the opportunity to raise your hand if you have a question in the end. Today's speaker is Mircea Kotlet from the Center for Functional Nanomaterials. His lecture is titled Ultrafast Studies of Optically Active Low-Dimensional Nanomaterials. And now I'm very happy to give the word to Chuck Black, the director of the Center for Functional Nanomaterials, to introduce Mircea. Please go ahead.
Great. Bjorn, thanks very much for that introduction. And I'm just going to follow on what you said by way of introducing Mircea, who I'm very happy to be introducing today. Dr. Mircea Kotlet, as Bjorn mentioned, is a scientist in the CFN. Let me tell you a little bit more about Mircea and why it's so special that we have the chance to listen to him. Mircea was a really early hire by the CFN. He joined the CFN in 2007. We were able to lure him away from Los Alamos, where he was a junior staff member there after completing a postdoc. Prior to being in Los Alamos, Mircea did postdoctoral work at Harvard and as well as Los Alamos, and graduated in 2002 from the Catholic University of Leuven in Belgium. So like I said, Mircea was one of the first staff scientists hired by the CFN as we were standing up the center. And essentially we gave him an empty room and we said, you know, we think the CFN should have an advanced optical microscopy facility. So why don't you do that? And it was a big task, right? And you're going to be hearing about some of the results of Mircea's work. He's built a highly successful facility, and supported many users in helping them do their research. But he's also demonstrated the value of those kinds of capabilities in pursuing the research program he'll be telling us about today. From the very earliest time in CFN, Mircea had ideas about the role of optical spectroscopy and microscopy in understanding quantum properties of low-dimensional materials. Of all the types you'll be hearing about today. And he has been at this for a while, and I would say it's really coming into focus these days because of the clear role these materials are being shown to have in quantum information sciences. So the groundwork he's been laying for many years is really coming into focus in terms of its applicability and pointing the future in this exciting new area of nanoscience. His work has been recognized most recently with the 2020 Brookhaven Science and Technology Award. And prior to that, his inventiveness recognized with the Battelle Inventor of the Year Award in 2019. So Mircea, we're really proud of you in the CFN and happy to be supporting you here, and look forward to hearing about your presentation today.
Thank you so much, Chuck, for your very nice introduction. I'm going to switch to the presentation, and before I go, all right, I hope I'm okay now.
Yeah,
Yes, you're good.
All right. I would like to thank also the Brookhaven Lecture Committee working with me, and also some of my colleagues from CFN in preparing this lecture. Like Björn said, it's a little bit different. I hope I'm up to the task. Title might be a little bit intimidating, but I'm going to try to walk you through some of the basic notions. One of them being, active low-dimensional nanomaterials. We talk a lot about nanoscience at the lab. Think about flexible electronics. It's something that we're very much excited in grabbing basically and having in our hands, for example, like curved quantum dot TV. This couple of years ago, this would look like science fiction. Now it's a reality. How about bendable smartphone might soon become a reality for the consumer. Also, flexible solar panels, or even more flexible medical devices. We can see nowadays like wearable smart watches having AKG sensor, motion sensors, electronic skin sensors, basically. What all these devices have in common, all these devices function on applications which are based on active low-dimensional nanomaterials. So, for example, if we take this flexible solar panel and we look a little bit more in detail at them, I would say microscopic scale, what can we see here? See this kind of picture here, where the active material in this electronic devices, which can be a field effect transistor, light emitting diode, solar cell, or a photoresistor, it's an agglomeration of nanoparticles between 2 and 10 nanometer, which we call quantum dots. So these materials have the ability to strongly absorb light and create charges, basically, which can then be used to as active materials in this kind of solar cell. So, for example, light emitting diodes, like type of the LED panels that I showed you, or screens for TV, basically. So that's a nice example of low dimensional nanomaterials. But going down to the basic is actually, what do we actually mean by low dimensional nanomaterials? If we look on Wikipedia, definition is really straightforward, but not that much explanatory. So it's materials or structures with at least one dimension below 100 nanometer. What does it mean? We look at this axis here, and we see that we can define materials that they have all the dimensions below 100 nanometer. We call them zero-dimensional nanomaterials. So they would basically, in this picture, occupy this particular spot here. 1D materials, 2 of the dimensions are below 100 nanometers, so they will occupy this small volume. And 2-dimensional materials in which one of the dimensions is below 200 nanometers, so they would be in this plane here. So based on this definition, we can actually think of cataloging nanomaterials or low-dimensional nanomaterials in what? In nanoparticles, for example. I already introduced quantum dots. We know about metal nanoparticles, colloid gold or silver. Fullerenes I will introduce during the talk, and like I mentioned, colloids. So these are materials that all the dimensions are below 100 nanometer. Nanowires, examples are quantum wires, which I'm going to discuss today, metal nanorods, or carbon nanotubes that are more known in applications like even in aviation industry as composite materials. And maybe nanoplates are a little bit more exquisite, I would say, more sophisticated, but we know about graphene. I will introduce graphene, van der Waals materials, 2-dimensional van der Waals materials, and briefly mention about perovskites. So if you look at these 3 categories, we have particles, wires, and plates. Those are materials which come from the bulk definition, basically. So materials which we are capable of seeing them. So we just add the word nano, and we enter a completely different world. It's not only the size that matters for this material, but actually, I will show you the physics becomes completely different when we go at nanoscale. Of course, there's a vast majority of low-dimensional nanomaterials. Today, I'm going to basically refer to one particular category, which is low-dimensional semiconductor materials. I want to bring up a cover article that our group recently published And this is a very nice example in this journal, Particle and Particle System Characterization. It's a nice example that sums up all three types of materials I just introduced in the previous slides. So we have zero-dimensional materials in the form of quantum dots. We have one-dimensional nanomaterials in the form of quantum wires or quantum nanorods. And those two materials, they sit on a two-dimensional material where all these spheres here are atoms, actually carbon atoms. So this two-dimensional material is nothing else than graphene. And it's also suggested in this picture that light will induce interactions between these components in the form of, like, for example, here, transfer of a charge from the quantum dot into the 2D material, which is one of the processes I'm going to discuss today. So coming back, going from bulk material to low dimensional materials in the case of semiconductors, and not only, the properties change dramatically. In this particular case, I'm talking about optical and electronic properties, and this happens because of the quantum confinement effect, which I'm going to try to explain. But in order to do that, I have to introduce the notion of the energy band gap for those people that are not that familiar. So, materials can be categorized in insulators, semiconductor, and metals. In the case of semiconductors, electrons, they tend to occupy regions in the materials that they have specific energy, and that is called valence band. And following optical absorption of light, these electrons can be promoted in conduction band, where again they can basically occupy specific energy levels. But there is a 4-bit region here, which we call band gap energy, which in turn defines the absorption and emission properties of a particular semiconductor. Now, going from the bulk to the quantum dot, because we take a material and we squeeze it basically in terms of dimension, making it smaller and smaller and smaller. Now the electrons in the valence band and in the conduction band cannot occupy any energy level. So basically, we don't have a distribution of density of states, basically, but we have specific energy levels that can be occupied in the conduction band and in the valence band. As a result, transitions between the valence band and the conduction band are highly specific. And as a result, actually, the particles that we create inside following optical excitation, which we bound electron and hole, which we call excitons, they have specific properties. What does it mean in terms of electrical and optical properties? It means that for the quantum dots in particular here, they will specifically show size-dependent optical and electronic properties. If you look at this figure here, we have a series of quantum dots where we change the size from something like 5 nanometer all the way below 3 nanometer. If you look at the specific band gap of this material here, so the difference between the valence band and conduction band, this band gap enlarges with a decrease in the size of the quantum dot. What does it mean that? We need more energy to create electron-hole pairs when we decrease the size of the quantum dot. And this energy increases as compared to the bulk counterpart. The effect on the optical properties is, if we look at this cuvettes here, where we have this quantum dots dissolved in some solution and irradiated with UV excitation, is a changing color with a changing size. So going from large quantum dots, we see the color red changes all the way into the blue, all the way to cyan. And now you have a nanomaterial, which is basically of the same composition, but through size, you just can control very well the optical and electronic properties. And that, for first thing that comes in your mind is like, I have the same type of material, which I can basically synthesize, control the size, and create a variety of emitters coming out of this material. So going back to the LCD that I showed in the beginning, to the quantum dot PD, because of this narrow spectra that we have here, narrow emission peaks, you can get to the point that you create really like crisp images out of this nanomaterial state. In terms of surface chemistry, this is a very important property of these materials. They can be easily synthesized. I will not go in details, but basically they are synthesized out of atoms connected with ligands. So through nucleation, we can grow the core of the the core can be grown. So in this way, we modify the optoelectronic properties, and then we can create shells around the quantum dot. And these shells are very important, one, for protecting quantum dot properties, the optoelectronic properties, two, for connecting the quantum dot with the outside world. And when I say outside world, it's something like, for example, what we call acceptor material. So like I mentioned before, quantum dots, they can absorb light, they can harvest the light, create this quasi-particles, extons or electron holes. So the mission here is to extract electrons and holes out of these cores and to create things like solar cells, basically. And in doing this, basically, the chemistry that we can do at the outside world of the quantum dot allows us to connect to a variety of acceptor materials. And here is an example here where we have a series of quantum dots of different size connected with, for example, oxides, which are known as good electron acceptors. So in this picture here, what we create or what is created is a series of what we call donor acceptor pairs, where controllably the electron can be expelled from the quantum dot core following optical excitation into the oxide. So this is the principle of functioning of a solar cell, and actually these hybrid materials, they do have application in this particular case. So we can talk now about quantum dot light matter interaction for this particular nanoparticle. And I want to play you a video here. I hope this works. I had a little bit problems, but this is a video that shows isolated quantum dots under a microscope, an optical microscope, actually more specific, a fluorescent microscope, where one can see what happens with isolated quantum dots when they are illuminated by continuous light, basically. So these quantum dots, they show this stroboscopic emission, so which we like to call it blinking, basically. Looking at this phenomenon here, the blinking, actually, if you look at a single particle and you monitor the emitted signal, basically in this case we call luminescence or fluorescence, we see that in time this signal goes on and off, basically, and occurs like burst, basically. So while one would expect that continuous irradiation should provide for the single quantum dot continuous emission, it's not the case in this particular case. And also it's noticeable that this on-off switching of the quantum dots is not a periodic function, basically. We can draw a line here and define this as the on time when the quantum dot is emitting, and we can define this as the off time when the quantum dot is non-emissive. And what stands behind this process, basically, is nothing else than charging and neutralization of the quantum dot. So basically, when the quantum dot is neutral, absorbs an optical photon, absorbs the photon, creates this electron hole pair, which we call exton, which can recombine and emit a photon. So we have an on level here, but sometimes the electron can be ejected from the core, so it can be trapped at the surface, and the quantum dot becomes charged and undergo non-radiative radiation. In this particular case, we will see something which we call off state or off time. And this process is reversible. This is what the arrows here show, and goes on and off and on and off. And if we look at the picture here, time scale, we can see that actually it has a distribution on off times and on times. So what we want to say is this blinking for a single quantum dot or a few quantum dots spans the time scale from milliseconds to tens of seconds. So it's really like a process that goes over a couple of decades. But if we look deeper in the quantum dot light matter interaction, actually we find out that besides the blinking, there is a variety of processes that a quantum dot can undergo. And I don't want you to, I'm not going to go to recite all these processes. What I want to stress here is the time scale that these processes go over. So from femtosecond all the way to microsecond time scale. And now we add the blinking, that is millisecond to second and tens of second time scale. So we really have like decades of time for processes going on in quantum dots. So what does it mean? That this is a big motivator for our nanoscience research at CFM, like Chuck was mentioning, from twofold, basically. One is we need to investigate ultra-fast optical processes at nanoscale in these materials. and composites that we make out of these materials. And at the same time, we are highly motivated to develop techniques or methods that we call ultrafast nanoscale optical tools to be able to resolve this kind of processes over such a wide time scale. Quantum dots are extremely nice nanoparticles. We have been studying them for over a decade. We're also interested in two-dimensional materials, in particular two-dimensional van der Waals materials. These are materials where atoms are strongly bonded in plane, like chemical bonds basically, but planes, adjacent planes, basically, they are stuck together through weak dispersion forces, like van der Waals forces. So that means we can use mechanical exfoliation or mechanical methods to separate layers between themselves. And this has been done, for example, for graphene. So we have graphite here, we use Scotch tape, and we can isolate a single layer of graphite, which we call graphene. If you could do this before 2004, probably you would be part of this team that won the Nobel Prize in Physics under Game and Konstantin Novoselov in UK for the isolation of the single layer graphene and for studying and finding out that actually it has amazing property. It has a high in-plane electrical and thermal conductivity. It's one of the strongest materials on Earth and actually has some sort of a semi-metal characteristic behavior. So it's a semiconductor, it's a band gap-less semiconductor material. Graphene is not the only one material of interest. If we look here, there's a variety of materials that we call 2D materials beyond graphene. Some of them, they have insulator properties. Some of them, they are superconductor. What we are interested to study are semiconductors, and in particular, the ones here, which they have a band gap in the visible. So these materials can be exfoliated at a single layer, so an atomically thin layer, and I'll show you becoming low-dimensional semiconductors, 2D semiconductors, what kind of properties they can show. So transition metal dechalcogenides, they have basically the formula something like MX2. M is a transition metal, can be found in this group here. X is a chalcogenide, sulfur, selenium, tellurium. Some of these materials, when they are exfoliated from bulk into the monolayer, you can see here, if it's squint, you can see a monolayer, they show what is known as indirect to direct band gap transition. So for example, doped silicon is an indirect band gap semiconductor and has to have some sort of thickness in order to absorb enough light. When a material becomes direct band gap, following optical excitation, the recombination of electron and holes that we create in that material happens to radiative, so it emits light. And because going from bulk to monolayer, one achieves such strong absorption and emission of light, we can see here for molybdenum disulfide what is the emission from a single layer versus a two layer, so there's a considerable difference. Now, I have a atomically thin layer, a 2D material that is highly absorbing and highly emitting. The first thing I can think of is I can make solar photovoltaics, which are extremely flat and flexible. I can make light-emitting diodes, but moreover, one of the recent properties of these materials, I can make sources for quantum computers, which we call single photon sources. So these materials are amazing. I would say by themselves, but how about combining them? So this is the product of our research. The idea of the research in our group is to create functional heterostructures. So we like to create new or improved functionality by combining low-dimensional semiconductors in the form of quantum dots, nanowires, with 2D materials. And one of the reasons is having a 2D material that's a bottom surface where you can grow things, basically. So we can follow up a bottom-up approach in building structures here. And kind of structures that we are interested in are the ones we call mixed dimensional heterostructure, like XD2D, where X can be 0-dimensional. In particular case, for example, like putting quantum dots or proteins on a 2-dimensional materials, nanowires on a 2-dimensional materials, or, for example, you can put a 2D material on a thin film polymers to create this kind of structures, 3D, 2D structures. We are also interested in creating more difficult but more interesting structures like heterojunctions out of 2D materials of different properties, and we create lateral heterostructures, or we can create vertical heterostructures. So by doing so, we are very interested at the boundary conditions here, at the interface, what kind of processes can happen, what is the this boundary condition affecting the optical and electronic properties, and eventually if emerging properties can come out of such structures. And this brings me to, I would say, today's talk, maybe an overview about today's lecture. I will touch base on two particular topics. One is quantum dots hybrids, where I'm going to show you some examples how to connect quantum dots with a variety of molecular acceptors, and to control what type of charge can come out and how fast the charge can come out. We do that by energy band gap engineering and molecular scale assembly. And the second topic is optically active 2D structures. And I will show you how we can control this interface to decide what kind of process happens between various low-dimensional materials, energy transfer or charge transfer. In many of our studies, we use, like Chuck mentioned, time-dissolved optical nanoscopy or variety of ultrafast microscopy methods. I'm going to briefly introduce two techniques here. One is transient emission microscopy. This is a picture of home-built instrument in our facility, where sample comes in this cryostat here. Lasers are input in this inverted microscope, and we can do spectroscopy studies and also ultrafast studies here. It's an inside picture of the ultrafast detectors that we use to monitor the intensity. So on this instrument, we basically acquire this kind of images. These are isolated quantum dots that are imaged through their emission fluorescence, and then we probe for each isolated quantum dot. We can monitor the emission intensity. This is a time scale of microseconds to seconds that we can address here. And also, since we do time-dissolved measurements, we can access faster time scale in the picosecond to nanosecond time scale. So this information is very useful in deciding the type of interaction, the rate for a particular interaction of this nanomaterials. Recently, we built a transient absorption microscopy. This is a more elevated instrumentation that allows us to investigate not only emissive nanomaterials, but also just absorbing nanomaterials. It's a palm probe experiment where basically we investigate the excited state absorption of a material. In this particular case, an example is shown for a monolayer MOS2, where this image shows the ability to spectrally resolve, so energetically resolve versus time resolve extons in a monolayer MOS2, basically. At various times, we can see different extons in this material. So the combination of these two techniques is very powerful in learning about ultrafast dynamics of this nanomaterials. So let's go for the first topic of today's talk, nanoscale charge transfer with quantum dots. The picture here shows a quantum dot with valence band, conduction band, and coupled with various acceptor materials, for example, fullerene, carbo-60 here, where electron transfer is promoted, or with a conductive polymer, or actually with a thin film of titanium oxide. So through molecular linkers, through optical inactive spacers, through the changes that we can do to the quantum dot nanoscale structure, I'll show you how we can control the type of charge transfer and the strength of that charge transfer. And in doing that, we have kind of like simplistic, I would say, design or path that we follow. We look at the charge transfer rate here on the donor acceptor system, and we see that in the most simplistic way, there are two terms here. One relates to the energy band gap overlap between the two constituents, the donor acceptor here. For example, in this particular case, in this image, is going to be the conduction band between the donor acceptor. So if we can vary this gap here, we can vary the driving force for the charge that moves from the donor to the acceptor. There's a second term here, actually, that relates to the distance between the donor acceptor or donor acceptor distance. If we can vary this, we can also control the charge transfer. So we have two ways: energy bandgap engineering and distance engineering. Energy bandgap engineering, we can mainly do it through the quantum dot. Like in this case, for example, we can use type 1 quantum dot, where the electron and holes are highly confined by a higher bandgap material like zinc sulfide. So it's harder for either of the charges to leave the core, basically. So we can promote different processes like energy transfer in this case, or type 2 quantum dot, where actually the electron and the hole are promoted to go into the acceptor material. Or we can design donor acceptor structures of the type 1, where both electron and the holes are expelled or ejected from the quantum dot, photoexcited quantum dot, or either the electron, in this particular case for type 2 band alignment, or mainly the hole are ejected. So depending on which charge you want to eject out of the photoexcited quantum dot, you can design this kind of procedures. In our studies, quantum dots are always the donor counterpart of a given pair. Details about these studies are published in two perspectives that came out from our group recently, one in ACS Omega, one in ACS Energy Ladder. So for those who want really details about these studies, can consult it. We can also do donor acceptor interface engineering. So basically we use optically active spacers to introduce between donor acceptor in controlling the pair distance. One such example is we use quantum dot core engineering. In this particular case, we have quantum dots of varying size, like I said, and we vary the size of the quantum dots. We vary this band gap here. So from large to small quantum dots, we just increase the band gap. As a result of this manifestation, if you look here in the emission spectra of the quantum dots, we see that the decrease in the core size shifts the spectrum towards higher energy here. In this quantum dots, we use a molecular linker to attach a very good electron acceptor, fullerene. It's a derivative. So photoexcitation of the quantum dots is going to promote an electron into the fullerene. So measuring the quenching of the quantum dot in the presence of fullerene, we can basically quantify the strength of the electron transfer. These distributions are lifetime distributions, which are indicative of the strength of the electron transfer. The ones colored relate to single quantum dots, basically. So if you look at the lifetime values here, what this mean peaks for red quantum dots, when I say red emitting, yellow and green, they are pretty much similar. But when we couple them in the acceptor pairs, basically we see stronger quenching with decrease in the size, basically. So calculated rate for electron transfer, we see that by decreasing the size of the quantum dot, we actually increase the rate for electron transfer in a very controllable way. We can do quantum dot shell engineering, basically. Here's an example of a core shell quantum dot, type 1 core shell quantum dot that is coupled with a conductive polymer. The band's alignment is chosen such that optical excitation of the quantum dot alone promotes a hole into the polymer. So the polymer is a hole scavenger. Now, if we put a higher band gap material here, like zinc sulfide, what we do, we create a tunneling barrier for the electron, for the hole actually moving from the quantum dot into the conductive polymer. And as a result, we can control how fast or how slow the hole moves from the quantum dot into the polymer. So in doing so, we created a series of quantum dots with the same core size and different shell thicknesses here. We can see that the quantum dot increases, the quantum yield of the quantum dot increases with the increase of the shell thickness. That's just the effect of the passivation. But when we combine this and we look at the transient emission images here, when we look at the quantum dots alone on the surface, on a non-interacting surface like glass, quantum dots basically, they do show emission depending on the shell thickness. But when we combine them with the polymer, which is a whole acceptor, we see complete quenching for very thin shell, some quenching for intermediate shell, and no quenching for thick shell. So in calculating the rates for hole transfer in this particular case, what we see here rate versus shell thickness, the rate decreases considerably with the increase in the shell thickness. If one wants to use such a hybrid quantum dot in developing solar cells, basically one has to think that I should have like 0 shells or no shell, because then charges are expelled or ejected from the quantum dot in a very fast way, basically. Some other examples here, not necessarily band gap engineering, but using donor acceptor distances, quantum dot connected to the carbon-60 that I introduced on the previous slides. We use this varying linkers, alkane tile linkers, where the tile connects to the quantum dot, connects to the carbon-60. When we compute the rate out of the lifetimes, we see exponential dependency, which tells us we actually can control the rate through these linkers. And at shorter linkers, of course, obviously, we obtain stronger electron transfer. Similar, we can design systems based on near-infrared absorbing emitting quantum dots like lead sulfide, where we have electron transfer with the titanium dioxide thin film. Quantum dots on glass, which is non-interacting, they show long lifetimes in the microsecond time scale. When we put them on titanium dioxide, we see quenching, so the lifetime becomes extremely short. Adding a dielectric layer of aluminum oxide actually slows down the quantum dot. We tell us we can control, through the addition of this non-interacting layer, the ejection of the electron from the quantum dot core to the titanium dioxide. Just to summarize for this first part of the talk, basically we can create new or improved functionalities by making hybrids and heterostructures composed on low dimensional materials. We can do band gap engineering and assembly to produce quantum dot sector hybrid with regulated charge transfer properties, and we can use a variety of acceptors to develop hybrids for desired functionality. I just gave an example for photovoltaics, the quantum dot connected with conductive polymers. We can do LEDs or biosensing. And moving further to the second part of the talk, I would like to give you some examples where we can do band gap engineering to decide what kind of interaction we have within the quantum dots, energy transfer or charge transfer with the 2D material. This is one recent example where we created quantum dot 2D material heterostructures. And in doing the interface engineering here for various optoelectronic applications, we were very much interested to see how can we promote either charge transfer or energy transfer between this type of low dimensional semiconductors. And not only that, but which of the two designs is better for a given application? If it's the whole transfer functioning or it's the energy transfer functioning of the two designs that are. And we opted for attacking the quantum dots, basically. So we used core quantum dots. And the energetics of the core quantum dot in this particular case with the 2D material, which is molybdenum disulfide, allows a hole to move from the photoexcited quantum dot into 2D material. While for the core shell, because we have this high band gap material, we only can transfer the whole pair electron bound to the hole, which we call exton, into the second material. We do optical and electrical imaging. Electrical imaging, we call it scanning photocurrent imaging. In this particular case, the material ends up to be active part of a field effect transistor, and a tightly focused laser is scanned over the active area. And an image basically that shows the photocurrent as a function of position across the device is shown here. Most activity at the source and drain electrodes. This is a reflection imaging showing the device basically with the active area with the 2D material and the quantum dots here. We can take these devices and do transient emission imaging that will tell us how strong is the interaction between the quantum dots and the 2D material. Quantum dots on a non-interactive substrate, they show long lifetimes, which are indicative of no interaction. But once they're on this 2D material, we see the lifetime is completely quenched, basically, both for devices, hybrid devices based on core only and core shell, this function on Hall transfer, this function on energy transfer. So if you compute the rates from out of these curves here, you get quenching rates or quenching efficiency approaching 100%. So that tells us the process is highly efficient in both type of designs. We can do, like I said, photocurrent imaging, and we see that from the pristine device that has only the 2D materials to the device, hybrid device, or headed structure, we get an increase in the photocurrent, basically. So addition of the quantum dots in both cases, core and core only, will show an improvement in the created photocurrent. But what is the most interesting part coming out of this study is the fact that when you start to increase the amount of light impinged on this device, transistors, you see different behaviors for the two type of architectures. For the one functioning on core shell quantum dots, which performs energy transfer with the 2D material, we see that increasing the photoexcitation power, we create more and more photocurrent, while for the one functioning on core only quantum dots, there is some increase in the beginning, and then the produced photocurrent is inhibited, basically. And one explanation that we came with is, remember, photoexcitation of the quantum dot next to the MOS2 material moves just a hole into the two-dimensional material, so we are left with negative charges here. So the more photons we absorb, the more negative charges we create. So this will act as a photo gate on the two-dimensional material, inhibiting creation of external current space. And that's why we see this behavior here when we put more photons. So the photo gate is going to suppress the creation of the current. In the case of core shell quantum dots, there is nothing to remain in the quantum dot. Basically, we transfer electron holes together in the form of excitons. So the more photons we put in the device, the more photocurrent we're going to create. Measuring the responsivity, which is nothing else than the input, the optical input versus the electrical output of this device, we observe that actually devices for functioning on core-only quantum dots shows the highest sensitivity, which makes sense because they like extremely low light levels here. So they can be eventually used to develop photodetectors, while devices based on core shell quantum dots, they will produce more charges or more photocurrent when they see more information. So we can develop them for, we can utilize this kind of hybrids or heterostructures for solar PVs. Another example is the incorporation of biological motifs into this 2D heterostructures. For example, we have been inspired by light harvesting, natural light harvesting antenna, which are collections of chromophores that they undergo energy transfer. And in the final step, the charges are separated through electron transfer to a reaction center. So we have imported this protein from a cyan light harvesting system, allophycocyanin. It's a donut-like protein, which is very flat, basically. And we came up with this design. We have a 2D material on which we basically lay down this protein, and on top of the protein, we have a quantum dot. So the idea is the quantum dot will absorb light, transfer to the protein, which has chromophores. There's chromophores in the pocket. And then the final step is going to be a transfer into the 2D material, in this particular case, molybdenum disulfide. For this to work, we have to do bandgap engineering. So we have to choose the quantum dot and the 2D material to match the optoelectronic properties of the protein in this particular case. So we would like to promote like a directional cascade energy transfer. And of course, behind this structure here, there's a lot of self-assembly and connection of this components. Shown here are pictures of the 2D materials, 1 layer, 2 layer, 3 layers that we exfoliated. It turns out that molybdenum diselenide is very brittle and hard to exfoliate compared to molybdenum disulfide. And once we add proteins and quantum dots, we see quenching coming out. We can probe dynamics here, and we see that the strongest quenching we obtain for the component here where we have quantum dots, proteins, and the two-dimensional material, which tells us that's the strongest interaction in the system, which basically is the situation that we want to have. Because when we make devices out of this components, we see when we measure the responsivity, the spectral responsivity, we get the Hertz values for this ternary system, quantum dots, protein, and the two-dimensional materials versus the bicomponents where we have quantum dots 2D material and protein 2D material. So adding the biological motives in this particular design actually increases the interaction and the sensitivity of the resulting device that we created. And final example that I'm going to show today is graphene conductive polymer hybrids. Graphene, like I said, it has high conductivity, but I think the absorptivity of this material is somewhere like 2%, and this has to do with being a semi-metallic band gapless nanomaterial. One can add the conductive polymer, which is a stronger absorber, on top to improve the responsivity of this material. So we can drop cast or spin cast a very thin polymer film on top of graphene, make a device and measure the responsivity. But how about if we can further improve the detector performance by changing the polymer morphology? So we go from a thin film, like in this case, on top of the graphene, we go to something like a mesh, nanowire mesh. So we deal now with nanowires out of the polymers, basically. And in doing that, we can apply a method called whiskers method, where the polymer dissolved in a good solvent is thrown into a bad solvent, and it forms this basically structure, mesh structure formed out of nanowire compared to a drop cast polymer of the same material. Controlling the concentration of the polymer and the molecular weight, you can get these voids to in this nanowire mesh to dimensions similar to the wavelength of light. So that will create a lot of scattering and rescattering and reabsorption of light, both into the conductive polymer and into graphene, basically. And that is supposed to increase the sensitivity of or responsivity of the material itself. And if we look here at the absorptivity of the nanowire mesh polymer versus the thin film polymer, we see that it's dramatically increased here compared to the thin polymer film. And here we compare polymers of polymer films of the same thickness. Making devices out of this hybrids, we see that for the nanowire here in red, it has the highest responsivity versus the thin film polymer and versus the pristine devices that are based on single layer graphene. So a straightforward method to move from thin polymer film into a nanowire mesh where controlling these voids can produce substantial improvement in these properties. And this brings me basically to pretty much the end of my talk today. So in summarizing for this examples of 2D heterostructures, I show you that bandgap engineering of quantum dots, MOS2 heterostructures can be performed, can be perfected for either solar PV or photodetector applications. We can bring organic, biological, and inorganic components to through self-assembly with 2D materials to achieve directional energy flow, improve optoelectronic behavior, and you can also use like self-assembly and creating this mesh-like structures to improve the performance of the photodetector. So coming back to the pictures I showed you somewhere the middle of my talk, so far we have demonstrated that we are able to create these structures with improved or novel functions based on 0D 2D materials, 1D 2D materials, and 3D 2D materials. And we can go further in looking at the 2D heterostructures in view of the fact that CFN is almost finalizing the a robot press, a quantum robot press, QPress, which will be very helpful in our research, basically. And new research direction at CFN in our group. So we are very interested in looking at ultrafast studies in 2D heterostructures. Heterostructures of different materials can be created. So in this particular case, the exton, the electron hole, can be spatially delocalized, basically. So one electron can be on one material, hole can be on another material. We're interested actually to intercalate layers in between this material, active materials, so non-active layers, to see if we can slow down the recombination of the electron and hole, so make the lifetime or the excited state of the lifetime of the exton longer, which is a property that counts for their applications in photonics and quantum information science. A structure is shown here, which has been built by a colleague of mine with actually molybdenum disulfide, tungsten disulfide kept between hexagonal boron nitride, and the band gap alignment here promotes this kind of formation of strong interactions, and the ability to do studies, transient absorption studies, where you can measure donor, acceptor, and donor together with acceptor to see a lot of dynamics. These are unpublished results, so I don't want to comment too much on them. And in terms of facility, basically facility development, we are trying to bring in magneto-optical characterization. So we're interested in combining materials with ferromagnetic properties with the semiconductors. So we need to develop particular facilities, and one of them would be ultrafast magneto-optical imaging and probing. This will allow us and users to perform a lot of spintronic, spin-exton interaction studies, and so on and so forth. And this brings me to my final slide, and I hope I'm in time. Acknowledgement, I would like to thank to my colleagues at CFN that helped me during various projects, my students from Stony Brook, collaborators from Syracuse University, Los Alamos National Lab, particularly on perovskite. I didn't have time to present them. And my very best friend, Eduard from Leuven University, from my former place, who helped me in developing transient absorption measurements. And thank you very much for listening to my talk. And I'm willing to take questions if there are.
Thank you very much, Mircea. I don't see any questions in the Q&A section yet. If you have a question, so please either type the question in there or just raise your hand and we can allow you to ask a question. So while people are still thinking about their question, maybe I can ask one thing. So in the title, you have this ultra-fast studies, right? So I was wondering, like, for which aspects of this research does the ability of, being able to do ultra-fast measurements matter the most? So you had these plots, right, on like slide 28, for example, where you have intensity versus time. Is it something like that, where you're able to resolve this nanosecond intensity, for example, or where does it matter most that you are able to do these ultra-fast measurements?
So it matters in this kind as well, the ability to do this ultra-fast measurements, but now more and more it matters for 2D heterostructures. Like the last examples I show, those processes are extremely fast, like picosecond time scale. And one of so the transient emission somehow gives up at extremely fast time scale. So that was one of the reasons we had to develop transient absorption methods, which are POM-probe-based methods, so we can go into the picosecond time scale to access processes like, electron cooling, or sometimes charge transfer can be extremely fast. So those are extremely useful tools.
Okay, thank you. Do we have any more questions? Please, you can just raise your hand. Yes, we do. let me allow you to talk. Tsang, I guess. Please go ahead.
Hi, Monsieur. Very nice talk. Can you hear me?
Yes, I can.
I see some of the slides you plot. In fact, this one is that plotting the responsitivity versus wavelength for all these devices. Most of them are higher than 1. We know that from silicon detectors, hardly can get to 1. How can I understand that?
I can refer you to my collaborator, Chang Yong. He is the device guy, and he can clearly answer these things. So I don't know if he's in the audience, but you know, we've been working. So for myself as a spectroscopist, what matters here is basically the relative values on these plots. Basically, so I'm looking which of the components under similar conditions performs better than the other components which I compare. For example, in this particular figure, I'm looking at the tri-component versus the binary versus the pristine component, which contains only the 2D material.
So on this particular slide, you showed responsibility is 1 to 2 on the y-axis. I think I saw the other slides, you go to many thousand. So I'm just curious, what's the meaning of that? And if you plot that as a quantum efficiency, would you show higher than 1 quantum efficiency?
No, that cannot. That cannot.
Something we missed. I don't understand. All right, thank you.
Okay. Any more questions? Please just raise your hand. I don't see any more. So if there are no more questions, I would like to thank Mircea again. Thank you very much. And with that, this was the 519th Brookhaven lecture. So thank you very much, everyone, for attending. Thank you, Mircea, and goodbye.